let's talk a little more about congruence. I have the basic definitions up here. So this first lemma, I'm going to leave the proof as an exercise, and it would be very good to exercise to work out just to get used to this definition of a congruence class and what it means to belong to a congruence class. So the setup is the same as up there. Let R be a ring. Let I be an ideal. Ideal, as always, unless otherwise stated, means two-sided ideal. Let B, capital B, be a congruence class. Modulo I, meaning it's a subset of R that looks like one of these sets. It has the form A plus I for some A in the ring. Then the following are equivalent. T, F, A, E, meaning the following are equivalent. One, that B is in B, and two, that capital B is B plus I, meaning it's the class of, which says that, so B in B means, in words, we say that little b is a representative for the class, or the coset B. So saying, what this is saying, that if you take any element of the class, you can name the class by that. So remember, in Z mod 5, this was a class. And then B is 2 plus the ideal. The ideal in this question was 5C. But you can also name it by some other element. It's also 12 plus 5C. It's also minus 3 plus 5C. Yeah, that's what this is saying. Part B. Let's give ourselves two elements B and C in R. Then the following are equivalent. First, that B minus C in I. This is same as saying B and C are congruent modulo I. Well, it's same as saying that B and C belong to the same congruence class. And that's same as saying that the congruence class of B is the same as the congruence class of C. Again, you should prove this in general, but all these statements should be familiar if you think of this example. In this example, at least, you know all these statements. And that should at least give you some sense why they are true. Okay, so I won't prove this. This is it's really just unpacking the definitions. If you need some help, look at that example that I'm just erasing right now, and it will tell you what to do. And again, just walking through through the example does not give you the general proof. The general proof will follow from the general definitions, but the example will indicate how to proceed. Okay. And the other thing that I want to say is the basic result that allows us to define an addition and a multiplication on the set of congruence classes. So remember, the set of congruence classes in our example was Z mod 5. And we had addition and multiplication defined on this set. And that's what we want to do in general. We want to define an addition and a multiplication on this set, R mod I, on the left-hand side, the set of all congruence classes. And this lemma will allow us to do that. Let R be a ring. Let I be an ideal. Let A, B, C, D be elements of the ring such that A is congruent to B mod I and C is congruent to D mod I. Then A plus C is congruent to B plus D mod I. And same for the product. AC is congruent to BD mod I. It's saying if two elements are equivalent mod I, two elements are congruent mod I, two other elements are congruent mod I, then their sums are congruent and their products are also congruent. Two statements. Let's call them. So let me just prove the second one. What is given? What is given is 4 elements A, B, C, D in the ring such that A is congruent to B mod I and C is congruent to D mod I. A is congruent to B mod I means A minus B is in I. Let's call this guy, I don't know, E, maybe X. And C is congruent to D mod I means the difference, C minus D, let's call that guy Y, is also in I. So A is B plus X and C is D plus Y, where X and Y are in I. And now I want to check AC and BD, so let's calculate AC. So AC is B plus X times D plus Y, which is, if you multiply out, BD plus BY plus XD plus XY. And now you notice that BY is in I. Why? Because Y is in I. And here comes the key property of ideal. If you take an element of the ideal and multiply by any element of the ring, the product is still in the ideal. So that's why BY is in the ideal. X times D is also in I, since X is in I. Same property, but on the other side. Take an element of the ideal, multiply by anything on the right, The product is still in the ideal. So by is in the ideal because I is a left ideal, and xd is in the ideal because I is a right ideal. And for this one, this is still in I, and you could say either. You could say it's because x is in I again. Okay, at any rate, the second and the third and the fourth term are all in I, so their sum, this is again in I, because I is a subring after all, so I is closed under addition. So what did we get? We got that AC is equal to BD plus some stuff that's in I. In other words, AC minus BD is in I. But that just means, by the previous lemma, AC plus I is BD plus I. That is, AC is congruent to BD mod I. Yeah, I suppose I don't even need to say this. Yeah, the difference being in I is exactly the meaning of, say, this statement, that the two things are congruent mod I. Proof of 1 would be similar. And I want you to notice that this lemma, this part 2 of this lemma that we just proved, is the first place where you use the property that I is actually an ideal. So the multiplication on R mod I is going to make sense because I is an ideal. So far, I think everything else that we did not only use the fact that I was a subring. But to make sense of this multiplication that we are going to define, you need this second part of the lemma that we just proved. And that crucially uses the ideal property right here.